Yes, welcome to Eeci GATE's Biomedical Gate 22 paper solutions. The next problem from analog electronics based on a MOSFET. So this is the given circuit. So in the given circuit diagram shown below, the MOSFET is biased in saturation. Already the NMOS is shown very clearly. It is biased in saturation. So very good problems. Okay, so I'm able to see in the biomedical paper to the level. Okay, so like easy paper. Even some problems went beyond circuit branches papers. Okay, like EEE and instrumentation papers, especially the op-amp based problems are really the level problems in the biomedical paper. I'll be addressing them soon in the next video. So, okay, yes. So let me get into this problem. So we have NMOS already biased in saturation. The MOSFET threshold is given, that is 0.5. That means it can turn on for any potential more than 0.5. That's what it means. Then W by L of the MOSFET is given, NMOS is given. So W by L is equal to 100 micro divided by 0.1. So 100 by 0.1. So let me check the unit, 100 micro. So this is 0.1 means it is going to be 1000. That's the ratio between width and length of the channel. Mu and Cox is given. So mu and Cox is given as 100 micro amps per whole square. Okay, so take it conveniently. It is given as V power minus 2. Okay, that's a given data. So if required, okay, so we have to play for the DC analysis. Okay, now you need that Kn. What is Kn of mu n Cox into W by L? Let me anyway keep this ready. So Kn is equal to of what is mu n Cox? So it is 100 micro amps per whole square into W by L, that is 1000. Okay, so that means the Kn is equal to yes, that's fine. Okay. So it is going to be 100 and this is going to be 1000. So it's going to become 10 power 5, 10 power 5 by 2. So 10 power 5 by 2 is nothing but 10 power 5 by 2 micro amps per whole square. That's what we're going to get. So we can make it as Kn is equal to 10 by 2 is going to be 5, 5 into 10 power 4. So let me take 5 into 10 power 4 as 50 into 10 power 3. So 50 milliamps per whole square. Let me take. We check. It is going to be 100 by 2 into 10 power 3. Okay, into micro. It's fine. Seems to be fine. It's milli. So 50. Yes, that's your K. So the Kn of this NMOS is known and threshold voltage is known 0.5 volts. It is biased already in saturation region. That's what he said. But we need the small signal equivalent. Okay, so to comment on the voltage gain raised by the problem. So assuming VA is equal to 1 millivolt, V in, let me take it is 1 millivolt as a small signal input to the MOSFET. The magnitude of the output voltage V0 is. That means so V0 can be negative or positive, but is looking for only the magnitude modulus of V0 in millivolts only, accurate to 2 decimal places. Ignore channel length modulation. That's what we usually do. Okay, so he didn't complicate the problem by giving channel length modulation. Fine then. So in fact, this is little easier than the gate 21 biomedical paper given. Okay, for NMOS. Okay, yes, we have to do the DC analysis. There is no other choice. We have to perform a DC analysis. So you have to switch off the AC signals. So at the end of DC analysis, you need not to prove that it is in saturation, but we need the channel current IDQ. So once IDQ is known, we can comment on GM. Okay. So what is your current ID when the device is in saturation? ID is equal to Kn into VGS minus what? V threshold of NMOS the whole square. So the GM is equal to 2 times Kn into VGS minus V threshold. If this is readily available, we need not to get into the DC analysis, we'll find the GM and we'll proceed. So it is already given in saturation. Therefore, to find out GM, to begin the comfortable small signal AC analysis, we need Kn that's readily available. And we need VGS, we need threshold. Threshold is already available. VG do we have means yes, switch off your AC signal. Then this potential is going to be 0 volt. it's a DC analysis, quick DC analysis. So the DC potential at this point is going to be 0, and this point at the gate is going to be 0.7. Therefore, the VGS is set to 0.7 volt. That's a VGSQ, where the device is operational and it is already given the device is in saturation. So I need not to perform a DC analysis. So this is where it is operating. It is operating at a voltage of 0.7. So then, okay, so here we need to find out the small signal equivalent, the transconductance. So what is GM then? So therefore, GM is equal to, let me find GM. The transconductance of the NMOS is equal to 2 times Kn into VGS minus V threshold of the NMOS given. So 2 times what is Kn given? 50 milliamps per whole square into what is VGS? VGS is 0.7 volt minus threshold, that is 0.5 volt. Therefore, the GM is equal to, it is equal to 2 times. Okay, this is volts, so it is going to be milliamps per volts, millisiemens or milliamps per volt. So 2 into, it is 50 into 0.2 you will get. So that's a number. So 50 into 0.2, so it is going to be, so 10 into 0.2, it is 2. So 5 into 2, it is 10. So it's going to be 20 milliamps per volts. That's your transconductance of the NMOS. So with that, we can get the small signal equivalent. With that, we can begin a comfortable AC analysis. So let me use small RS. This is your drain, this is your source, this is your gate. Okay, so this is your small RS, that is equal to 1 by GM. So what is small RS? We'll comfortably play with small RS. So small R is equal to 1 by GM, that is 1 by 20. So 1 by 20 into 10 power minus 3, that is going to become 10 power 3 by 20. Okay, ohms. Okay, so 1000 by 20, that is going to be 50 ohms. Small RS is equal to 50 ohms. Let me check the data once for any mistake. So it is 2 into 50 into 0.2. So 50 into 0.2 will be 10 into 0.2 is 1. Sorry, 2. So 2 into 5, 10. So it's 20 for sure. So RS will be equal to 50 ohms. Yes, let us begin the small signal AC analysis to find the V0. So switch off the DC sources. Okay, so we need not to play with that 2.5 volt battery. We need not to play with that 1.25 because they are influencing only the DC conditions. Switch off all the DC sources. Let us begin AC analysis. Okay. So 0.7 is made 0, 1.25 volt is made 0, 2.5 also made 0. Okay. So then the equivalent circuit will be this. Yes, let us switch off the DC sources. Then I will get V in applied to the gate terminal that is given 1 millivolt. Okay, it should be a instantaneous. So treat this as a small signal. Okay, it's 1 millivolt sin omega t, something like that. So you can take it, say either RMS or peak. Let me take, because the problem is only with respect to V in equal to 1 millivolt. Okay, so then we'll play for that. Assuming 1 millivolt AC applied, so to the gate of the NMOS terminal. So then the small signal equivalent of NMOS coming into play, where the small RS coming into play. So just connected before the source terminal. And remember, this is the gate terminal. Then what else is there? We have a 625 ohms connected at the drain terminal, and this is made 0 for AC analysis. Then The battery connected is also made 0. This is going to make your terminal V naught. Okay. This magnitude only we need to find, and the source is already connected to the ground, so therefore it is ground. And here we have a resistance of another 625. Okay, then 625 ohms means this 625 and this 625 both are connected to the drain. That is going to be 625 parallel 625. It is going to be off of it. Okay, it is going to be 625 by 2. Let me take. Okay, so finally we'll go for the evaluation. So then remove this resistor. Then combinedly you take it as 625 by 2 ohms. Okay, that's a resistance here. Okay, that's a net resistance. We'll go for the V naught. Then the problem is very simple. So what is a V naught in millivolts? Okay. So let us begin the analysis. AC analysis. So this difference we know it is equal to 0 as per the small signal equivalent, and RS is given, but the small r is 50. So this is equal to 50 ohms. Okay, so therefore this is 1 millivolt means, and this is also going to be 1 millivolt. Then the current is going to be 1 millivolt by small rs. Same current is here. That's my ID channel current. Okay, that's my ID. That is going to make a drop here. So let me call this as a capital RD. So that is going to be small ID into capital RD. That's a drop. So this is 0 volt. From 0 I am losing this. Therefore V naught equal to minus ID into 625 by 2 ohms. Okay, that's a voltage V naught. So V naught is equal to, substitute your I, that is going to be minus 1 millivolt by 1 millivolt by RS, that is equal to 50 ohms into 625 by 2. 625 by 2. So that's your V naught. V is already substituted. Therefore, V naught is equal to, what you get is minus 625 millivolt by what? 100. Let me take. Okay. Ohm will get cancelled. That's a resultant. Therefore, V naught is equal to minus 625 by 100 means it's going to be minus 6.25 millivolt. But he's asking only what? The magnitude of the output voltage, therefore in millivolts. So it is going to be 6.25 is your answer, up to 2 decimal places. Perfect. A well constructed problem, almost your common source configuration. So even if you remember common source configuration straight away, the current transfer takes place from small rs to capital RD. That is going to form your gain. So the gain is going to be this. Then V naught will be your gain times your Vn. You can also play with this. The gain is going to be from where to where the current transfer takes place. From small rs to capital RD, the current transfer takes place. With that, we can find the gain instantly, and then we can comment on the output. That's another way as well, instead of doing formal AC analysis. That's an interesting problem. Happened for the biomedical paper. Okay, yes. And hope you enjoyed this content. Yes, biomedical students, this is what the demand from you. Okay, so you have to be very familiar with the content of IN, the common content which is common to both IN and biomedical paper. Okay, yes, that's how you need to prepare. This is what expected from you. Okay, a good paper, maybe around 40 plus is enough to get into IITs. Okay, with this paper. So thanks for watching, and do subscribe the channel and look for the updates. We'll update you soon with one more problem. Okay.